we want to explain the difference between an absolute minimum and a local minimum. Well, basically, we are talking here about where we look at the function to talk about an absolute minimum and a local minimum. So when we talk about an absolute minimum, we talk about the image of the value where we have an absolute minimum is less than or equal to all the values of the function in the domain of the function. That is, the image of that point, or the point C, where we have an absolute minimum, is the smallest value of the function, that is less than or equal to all the images, but for all points in the domain of the function. So is the smallest of the images of the function looking at all the images in the domain of the function. When we talk about a local minimum, we are only looking at values of the function near some value c. For example, we say f of c is less than or equal to f of x for all x near the value c. That is, we normally take an interval, generally open interval, which contains the value z here, the value c, and then at that interval, we find that all the images are greater than or equal to the image of that value c, and so then we are talking about local minimum. But obviously, when we constrain or change or redefine the domain of the function, these definitions can overlap some way. But what is important is when we have defined the domain of the function, or the domain is implicitly defined when we know the domain of the function, then the smallest of all the images of the function is the absolute minimum. There's no doubt about it. But in the case of local minimum, we gotta see only near the value where the function attains that local minimum. So it's better to put some examples, and for example, we can see this function here. Let's say that the function has this domain I'm drawing here. That is, the domain is this closed interval AB, let's say. So we can see that the smallest of the images of this function happen here at the end left endpoint. That is, if we draw an horizontal line, we see that that image f of a is an absolute minimum because it's the smallest of the images of all the points in the domain, in this case in the interval AB. But we can also see that this value here, the image of this point, is a local minimum, and that's because if we look at that point here, let's call it C, and we stay, for example, near that value, we constrain our attention to this interval containing C, and then the graph of the function is only this portion here. There, this image, the image of point C, is the smallest of the image, let's say in this interval I, let's call it I. And for that reason, let's see, we have a local minimum. We cannot say, for example, that at this point we have a local minimum. It's not true that if we look close to this point only, the image of that point will be the smallest of the. At the contrary, this is at this point we have a local maximum. For example, let's put another interval here. Let's say we stay at this interval and we look at the function there. As you can see, there is no a local minimum in that open interval. That's why we have a function that is increasing in that interval, and because the interval is open, there is no smallest nor largest value. There can be also situations like this. Let's put this graph here that resembles a little bit to, looks like the absolute value function of x. And that graph, as you can see, if we look close to the image of 0, which is 0, doesn't matter how close you look, the smallest value is 0, is the image of 0. So that is here, f of 0 is an absolute minimum, because if you look at all the domains, suppose all the domain is the whole real line, it is the smallest of the values. It's an absolute minimum. But it's also a local minimum. If you look close to that point only, that is, you state at a portion of the graph that contains 0, of course. In that case, is again the smallest of the values. So that is, in this case, is an absolute minimum and a local minimum. And when we have several local minima of a function on a domain, then the smallest of all those local minimum is the global minimum, the absolute minimum, or the global minimum. But as you can see, we can have several local minimum, but only one absolute minimum. For example, let's put another example, something like, okay, if we have, for example, a function like this, let's say that, and the domain of the function is, let's put it like here, and the domain, let's say, is this interval here, AB. So we have this value here is a local minimum. If we look only around this value at some open interval close to that value, containing that value, we can see that that's the smallest of the values. So we have a local minimum here. We have also a local minimum here. And we can say that at B, but we want to talk about local minimum when we can put an interval containing an open interval containing the point where we say there is a local minimum. So we don't talk about the endpoints because we cannot put an open interval to the right, for example, of B. There is no function there. So local minimum are mainly inside the domain, and no more local minimum. These are the local minimum. But from all the graph, that is, if you look at the whole function and we choose the smallest of the values, then we have this absolute minimum. So here we have an absolute minimum also. So in this point, or at this point, we have a local minimum and also an absolute minimum. But in here, this point here, we have only a local minimum because the absolute minimum is here. It cannot be at this point. But we can have situations where we have several points where we have the local or absolute minimum, because one of the examples we know very well is sine and cosine functions. So here we have this function that is sine in this case. If we consider the complete function, that is the domain is the real numbers, then we can say that the absolute maximum value of the function is 1, but it's attained at several points. That's no problem. The theorem says that that is at least 1. So in this case, you can say that the function attains an absolute maximum value of 1, in this case, at infinitely many points, but we also attain the absolute minimum, -1, and at infinitely many points. But these points where we have an absolute maximum and absolute minimum, they are also local maximum and local minimum. That is this local minimum, because if you look close to the point, this is the smallest value, is a local maximum, this is a local maximum. So we can combine, there are several examples where we have the situation. So if we look, for example, another example here, we take a line, let's say, and if we take a line like this increasing and we don't include the endpoints, that is the domain is the open interval AB, then there is no local minimum, no local maximum, no absolute minimum, and no absolute maximum. Sometimes it's hard to understand that, but the thing is that if you say there is an absolute maximum value, then we can find another one that could be an absolute maximum. That is, when this is not included, we have the possibility of putting always a point in between what you say is an absolute maximum. So there's no absolute maximum. It's got to be closed in order to be sure that the absolute maximum or absolute minimum exists. And the continuity is the other essential property that guarantees the existence of the absolute maximum and absolute minimum. So when we have a continuous function and a closed interval, there is always an absolute maximum and an absolute minimum. So like here we don't have local minimum nor local, sorry, absolute minimum. So in summary, the absolute minimum of a function is a value x where the c in the domain of the function for which the image of that value is less than or equal to all the other images of all the points in the domain of the function. And a local minimum refers to the smallest of the value of the function, but not in the whole domain, but near the value c. Near means a relatively small interval around the value c, or in general an open intervals around containing c or around c, for which the image of c is the smallest of the images of that interval. And that's the main difference.